So in this lesson, we're going to talk about thermal expansion. We'll introduce the linear expansion formula, and we'll understand bimetallic strips and find uses for them. So first thing is thermal expansion. When things get hot from the previous lessons, we know that the energy increases. What happens is the actual object itself will expand. It will get bigger because the particles, as they're getting hotter, they will want to move away from each other. So a little pro tip for you is if you're trying to get a tight lid and you cannot open it, you can run it into hot water to make it expand a little, to make it easier to open. So there are two types of thermal expansion, linear and volume expansion. So the idea of expansion, as I mentioned, they get hot, the particles start vibrating more, they will need more space to vibrate, so it expands. The actual particles themselves do not change size. They do not get bigger. They just get spread further apart. So that's why it looks like it's getting bigger. The opposite happens when it's cooled. When you make something cold, the particles vibrate less. They need less space. That means it will contract. It will get smaller. So thermal expansion is the increase in size when you increase the temperature. The space between the atoms increases. So a rule that we need to use is the linear expansion formula. If you had a rod, just a long piece of wire or metal, it has a length, a starting length, L0, starting length, and a starting temperature. You will change the temperature. So I'm going to increase the temperature, which means when the temperature increases, it's going to vibrate more, it's going to get bigger, and now I have increased my length. The change in length can be found by taking the coefficient of expansion, which basically is the strength of the metal, multiply that by the starting length, whatever it was, and you multiply that by the change of temperature. You multiply them all together, you will figure out how much bigger this object has gotten. Different materials have different values of the coefficient. So this table will be given to you, the information that you need, so you do not need to memorize any of this. So here are a couple of examples. There's example 1 and example 2. I'm actually going to start with the bottom one because this does not need to rearrange the formula. The top one you will. So let's just quickly have a look at this one first. How much longer will a 300 meter steel bridge be on a 30 degree Celsius day in August than on a minus 10 degree night in January? So there's a change in temperature here, and we have the coefficient given to us. So I'm trying to find the change in length in this case. Okay, so to find the change in length, no problem, we'll take the coefficient and we're going to multiply it by the starting length, L0, multiply it by the change in temperature. So change in length equals 15 times 10 to the minus 6, which is the A over here. I'm going to multiply that by 300, because that's the starting length. And I'm going to multiply that by the change in temperature. It's 30 minus 10. That means the change is 40 degrees. Between 30 and negative 10 is a 40 degree change. Okay, so we multiply it together. We will have a change of length by about 0.18 meters. So if I asked you what the final length would be, all you would need to do is you'll take your 300 and you'll plus 0.18 to it, and you should get 300.18 meters, if I asked. So now let's look at the top one now. So in this case, we have the starting length of the bar, you have the temperature, you have a change of temperature here, and you found that it's 2 millimeters longer. What is the coefficient now? So you'll take this rule, if you remember what we did before, you will just divide both sides by L and T to take it to the other side. So we have our information, 1.6, we have the change in temperature, 90 minus 40, which is 50. You have your change in length, and now this says 2 millimeters, remember that's not good, it's 2 times 10 to the minus 3, or you can simply divide it by 1,000. Either way is fine, we can write it like this. So to find the coefficient, we'll take my change in length divided by L0 and T. We'll have 2 times 10 to the minus 3 divided by 1.6 times 50, and you should get 2.5 times 10 to the minus 3. Celsius minus 1 is the same as dividing by Celsius. That's the overall unit for the coefficient. So a use of this, something that we can actually use it for, is a bimetallic strip. At room temperature, you can have two strips, steel and brass, for example, next to each other. As the temperature goes up, one of them will get expansion. One of them will get bigger, and as it gets bigger, it will start to bend a little. So, for example, brass has a lower coefficient than steel, so brass will get hotter faster and it will try to expand. But it's stuck with the steel, so it will just start to bend around it. So, a useful feature of this means we can use it in a thermostat. When you have a set temperature, let's say 25 degrees, everything is fine. But as it gets hotter, you will see that brass maybe wants to expand, so it will kind of push outwards. As it pushes outwards, you can see that this connection has stopped, and now that can turn on the AC, for example, to make something cooler again. When it gets colder, it will go back again, and it will connect, and that will stop the AC. So that's just an example of a use of a bimetallic strip. This is also used in things like expansion joints on bridges. You will notice if you go over a bridge, you'll feel a tiny little bump as you're going at certain intervals. That's because you don't want the road to mess up. When it gets hot and cold, it will have room to expand and contract itself. And as I mentioned already, you can use it inside a thermostat as well.